Okay, today we will continue our discussions on self excited induction generators. In the last class we said it is an attractive option for standalone power generation, because there was a concept where induction generators were mainly meant for grid connection, whereas if you want a standalone you have to go for alternators or synchronous generators or permanent magnet machines. So, this is a result of considerable research which took place for last 30 years on this area, and instantly we started this work somewhere in 75 76. Okay. So, it is nearly 30 years of work. So, I am trying to compress the 30 years of work into less than 50 minutes, right. Okay. So, obviously, we have to we can only give you an overview of what has been done from concept to a technology development which has seen its utility in the field. Okay. Right. So, the system is you have a prime mover which is driving an induction generator, a 3-phase induction generator. Okay. Prime mover can be any prime mover, right, and you connect a capacitor at the terminals, right, and you also connect a load, right. So, the prime mover may be any prime mover, hydro, engine or turbine, or a wind turbine, etc. Okay, any type we have said it can be there, and it is a normal 3-phase induction machine. This generator is a normal 3-phase induction machine. Capacitor is the AC capacitor, okay, and the load can be any type of load, electrical loads which are isolated. It can be a resistive load or a RL load, okay. Usually do not have much RC load, okay, or it can even be nonlinear loads, okay, or a motor load, right. A load, electrical load, different types. Okay. Now, what we are trying to say is if the machine is driven at a speed, so what is the speed in which it is driving, speed and the capacitor you are connecting, okay. The machine parameters, the load, right. I want to know what is the voltage here, how much voltage it will be generating, and I want to know what is the frequency that will be here. This is the problem. Okay. You are driving from a prime mover, you have a machine which was a dead machine, you connect a capacitor, start driving it, connect a load, I want to know what is the voltage across this load, what is the frequency of the load, etc. This is the problem. Okay. Right. So, what we are considering steady state analysis, not the transient analysis. Okay. So, we take the steady state equivalent circuit of 3-phase induction machine, okay, and then this was the equivalent circuit we can use. We have already said that this will be the machine equivalent circuit that is the induction machine, right, and you have connected a capacitor. You have to model it like this. You have modeled the capacitor which is at the terminals of the machine, and you have modeled the load. I have taken here a purely resistive load. Okay. So, this you have done, okay. And if you look at this, one thing we say is there is a current here which is the stator current which is getting out of the machine, right. IS is the stator current, which part of it goes into the capacitor and part of it goes to the load, right, when it goes out. If you look at the simple circuit equation, because there is a rotor current here which you can't have an access, you can't measure the rotor current, it can only be because it is in the squirrel cage rotor, right. and it is running at the speed nu per unit speed, okay. And we discussed yesterday what we do not know. We do not know this xm which is saturated, and we do not know the frequency which is we do not know, okay. These in the circuit we do not know these two parameters, right. And we say, in fact initially we had lot of problem how to find out this thing. So we evolved a system, that is why a paper which was in IEEE in 1982, first paper we published, as I mentioned to you here, which in this it is explained how you calculate this, okay. And this has been referred by large number of people since last 35 years, okay. This is a very high citation index of this paper, okay. Now, these are the parameters you are aware of, okay. So, you know these parameters, and this you do not know, you want to find out. You know the capacitor, you know the load, right. Now, what we did yesterday was in the last class was we can load and capacitor, you can call it as Z load, okay, and the stator impedance you say Z S, and the rotor impedance simplify to Z R, and a current I S. So, we can always say the Z into I S by Kirchhoff's voltage law is 0, okay. That means where Z is nothing but ZL plus ZS plus ZR, okay. Is it clear to you? So, we have made 3 impedances, some of them should be 0, okay. Now, that leads to, okay, these are all the parameters which we have already seen, F nu, Vt, Vg are the terminal voltages, okay. And this Zs will be the load impedance ZL, which has a capacitor, it is a parallel combination of capacitor, the stator impedance Zs, okay, rotor impedance Zr, right. And we know that Zs Is is 0, but it is self excited, means it is having a current, means Is is not 0, therefore Zs is 0, okay. So, we have said that Zs is 0, right, which implies that its real and imaginary parts must be 0, okay. Its real imaginary part must be 0, and so that means we say one unknowns are xm and f. So, f of xm and f is 0, which will be a polynomial, okay, nonlinear equation, and g of xm and f is 0, okay. Is it clear? So, I want you to, the assignment I gave you today should be submitted in next 3 days, you derive this, right. This all of you has to do it, it is not that you copy from one to another, and any two identical things will be discarded, okay. You should sit together, I mean not together, right, you individually do it, right, okay. Now, these are the constants C1 to C2, I want you to derive, this is an assignment, derive this, these constants, these are all in terms of the parameters of the machine, okay. And again these are all you have to derive, this is the one, this is the assignment, okay. So, assume that you believe whatever I have done, okay, and these are the constants, right. Oh, sorry. Now, these are not solvable, two equations, two simultaneous equation non-linear. Therefore, one of the method which is considered suitable is the Newton-Raphson method. I think you are aware of you are all aware of Newton-Raphson method, okay, which are used for solving non-linear simultaneous equations, okay. And what you do, right. So, you know that what you have to solve is you have two equations f is 0 and g of x y is 0, is not it, right, and you do a Taylor series expansion, right. So, any point f of x y will be from an approximate x naught origin initial value x naught y naught plus delta f by delta x, okay, at that point into x minus x naught, right, plus delta f by delta y at that point into y minus y naught, is not it. So, this is Taylor series expansions. You will all say first derivative, partial derivative and multiply by the step, etc. You try to see at from the initial value you try to find out what is x y after a small displacement from x naught. Okay. So, you go on doing this and then you will then go to from another value x 1 y 1 which is approximately 0 or g x 1 y 1 is approximately 0, right, and you will have how you get it is that we have 0 will be equal to f of originally x naught y naught plus delta f by delta x at that point x 1 minus x naught plus delta f by delta y at that point into y 1 minus y naught, which is 0. Okay. So, you will say that I think the final delta f by delta x at the original value x naught y naught into that displacement h step h plus delta f by delta y at that value into step k, that means displacement in y should be equal to minus f of x naught y naught. Okay. That is what you will do. Okay. Now, similarly delta g by delta x of h plus delta g by delta y k is equal to minus g x naught y naught. So, this is how you do. Okay. I am just repeating those who have just a simple way. Okay. So, you finally get this what is a Jacobian matrix J11, J12, J21, J22. It is for 2 equations, of course, there can be n equations. I am just because we are interested in 2 equations will be equal to minus of f naught g naught, whatever was the value at the initial value. After initial value, you try to find the new value of x1, then that becomes initial value for next iteration and try to go on doing this. So, this into h and k. So, you will find you solve for hk, is not it? Sorry. Is it okay? I am just telling all this thinking that you already know it. Any doubt on this? So, what you do is you find out the value of these 2 functions, let us say f and g, by by putting the initial values and know the and you will know that its value will not be 0. Okay. Then you find out the next step which direction it has to go. It has to take you to 0. It has to take you to the root of these equations. Okay. So, you will know that original value x naught will now become x 1 which will be equal to x naught plus h and y 1 will become y naught plus k, is not it. So, you have now gone to the new value, okay. Then repeat or iterate, right. You go on iterate till you get a value that f of x y should be less than some small value epsilon, right, or similarly g of x y should be less than epsilon. Is it clear to you? So, what you do is you have these equations, assume an initial value, try to find out the step, so that that value will get added by that step, which can be plus or minus, okay. And finally, you would like to see that the function, you are having some value, let us say f g for different values of x y. So, you would like to take it from some non-zero value, you drag it towards its root, right, where the magnitude of these must be taken to the root. So, you have to find out what is that value of x y, which will satisfy these two equations. Is it okay? So, this is we thought that this is the best way for solving for this function, and since last 35 years many of people are using this method now. Okay. So, Jacobian, you are aware, this is the Jacobian matrix. Okay. Now, in this case your unknowns are x m and f, is not it. So, you know you have two functions f and g. Okay. So, J11 is delta f by delta x m, J12 is delta f by delta f, J21 is delta g by delta x m, J22 is delta g by delta f, right. So, what will be initial value? Guess an initial value, no. What will be initial value of x m? I call it x m naught, initial value f I call it as f dot. You must guess. What do you guess? Say, one thing is, what we have done is Newton's method requires the initial guess of values of unknowns x m naught and f naught. Okay. What we did was, let us guess the initial value of x m naught is, unsaturated value of x m, which is a linear range, because saturated value will be less than the unsaturated value. Start with the unsaturated value, okay, and you assume that the frequency is approximately equal to speed. So, you take the initial value of frequency as speed. So, if you are running at 1 per unit, you would say f naught is 1, but it will not be 1, actually it will be less than that. Okay. So, we know that h k will be the inverse of the Jacobian matrix and f minus f naught g naught, is not it. That means, you substitute these values for f naught is same function x m naught and say f naught, and g naught is x m naught and f naught. Okay. You assume these two values which you know, right, then you find out the step, you go on repeating it, okay, and then finally next step is to calculate the, okay, let me see, right. Iteration can continue till the desired accuracy is reached, that is, the function f of x m f must be less than a small number epsilon, g and f x m f must be less than a small number epsilon. Is it okay? So, you can develop a small computer program algorithm to see that for a given value of capacitor, speed and the load resistance, you can find this value of x m and value of f. Is it fine? So, you have solved that circuit. You now know all parameters of the circuit which make sure that Z s is 0. Okay. So, you have found the frequency also now. So, you know what is the frequency of the generated voltage, right. You know the frequency, but that is not the end of the story. You want to know the voltage induced. Okay. Then how do you do that? Okay. You have x m, you have f, but I want to know what is the voltage that I will get across the load, right. How will you get that? Okay. I have taken you through the routes of solving the equations and Newton Raphson, computer programs, digital simulation, everything, and you have got the now you have solved the okay. It should not happen that you have solved the equation, but still you do not get the voltage. Please think, can you have a machine, you have a capacitor, you have a load and it is machine is driven at a given speed, and now you have solved this, you have solved this equivalent circuit. You know the equivalent circuit parameters, the stator resistance, rotor resistance, stator leakage, rotor leakage. You also now know the saturated magnetizing reactance. You know the frequency of the generated voltage, but you just do not know what is the voltage that it will generate. Okay. You have the equivalent circuit in front of you. Okay. Do you think we have solved the problem, or we have a problem in hand? Huh? You do not even know we have a problem or not, is it? Is it clear to you that we have a problem? Huh? Right? Then can anyone suggest what can be the way out of this paradox, or way out of this problem we have faced? Because I think during the lectures I should give you some time for you to think also, right? Are you able to think?
We can calculate the voltage from the power.
I do not know the power. I say, you see, I have a dead resistance which is just connected.
Know the mechanical power that is given to the shaft.
How do I don't know? Engine is running. I don't know what mechanical power that fellow is giving to the shaft. I mean, it is much more difficult, because mechanical measurement is more difficult. I know the speed only. You can at most measure how much, if it is driven by an engine, I can at most say yes, it is consuming so much of petrol or a diesel or a kerosene per minute or something, that you can measure, but does not give me, and even that power is not the same as what it will give. In between there will be a lot of losses on the way, in the engine, in the shafts, in the friction bearings and various things. Okay. Because why I am posing this problem, we faced this problem when we started to solve this problem 40 years ago, 35 years ago. Okay. We did not know what to do, okay, after this. And that is why till that time not much, almost no papers were published in this area, because there was a problem unsolved. Okay. Can anybody can think, or you think you have saturated, like saturated magnetizing reactance. So, it is the problem is with the saturated magnetizing reactance. Okay. It is the saturation which creates the problem, right. Okay. Now, the next step is to calculate the air gap voltage Vg and the terminal voltage Vt, which requires the information regarding, see, Vg, Xm and the flux. There is a relation between the magnetizing reactance and the flux, isn't it, or the voltage, air gap voltage, this relation is there. There is this Vg by F, which is a measure of the air gap flux and the magnetizing current, right, and typically it is this how it goes, right. Okay. Now, the ratio of this is Xm, right. This is nothing but Vg by Im, we can, right. So, there is some information available to you if you know from which you should be able to estimate the voltage. Okay. So, what this is how it was more intuition at that time. I thought why not we try this trick, right. Try to get information on the no load magnetization curve, okay, variation with xm. I know xm, right. So, if I can plot in a different way, xm and Vg by f. How will this variation be? Unsaturated, it will have a as the low value of Vg by x, low value of air gap voltage, you expect the xm to be constant and unsaturated, right. So, it will be like this, sorry, this is constant unsaturated, is not it. Now, if you increase the Vg by x, increase the voltage means it gets saturated, the flux gets saturated. How will it change? Where will this be? Will it go like this or will it go like this? Will it turn to the left or turn to the right? Will it be turn to the left. So, therefore, you can expect, sorry, okay. So, you can have this is saturated xm, unsaturated xm, right. You have already determined some value of xm. So, you know some value of xm as calculated is computed. Okay. You have got the xm, you have got f and xm. Now, what we did was, why not we try for you have knowing this curve, for that xm what will be the Vg by f, okay, for this xm. So, we know Vg by f from xm, right. So, you know the Vg by f, and that equivalent circuit which we already have seen, which has Vg by f here, okay, and of course, rotor you are aware of that circuit, this will be IR J XLR RR over F minus nu, okay, and you know already now because you know the Vg by f here, and for that saturated xm, right. Okay. Then you have this resistance leakage of the stator Rs by f and J XL S, okay, and you have connected the capacitor here, this is Is, and you fix the load here RL by F, and this is your IL, this is IC. Now, with this potential being known Vg by F, and you know Xm, you know F also, right, you can solve it, isn't it, right, solve for all quantities, you can solve for IR, solve for IS, solve for IC, solve for IL. Is it clear? So, your circuit is totally solvable now. So, you have to, so from the curve Vg by F versus Xm and saturated Xm can be obtained, and with the knowledge of Vg, Xm, F, Xc, speed, RL and machine parameters known, then you can calculate the terminal voltage Vt, load current Is, okay, using the equivalent circuit, right, solve the equivalent circuit. Okay. So, these are the equations. For Is, this is the equation, you know Vg by F, and this is just a, you can verify from this, and rotor current, load current, terminal voltage is nothing, load current into resistance, is not it? You know the load current, you know the resistance. So, this is what you have Vt, okay, and input power is this as a generator minus Q times IR square RR or F. I think we have done it for the as a generator, where Q is the number of phases and output power is IL square RL. So, you can, so it is basically you can develop a program, okay, computer program. What you do is you start and read the parameters. What parameters that you know for the machine? Resistance you know, rotor resistance, leakage reactance, speed and capacitor, that is what you know, okay. Then you also take the minimum load, BL is the load, then you iterate, you take the initial value of xm and f, right, initial value of xm and f, then calculate the constants C1, C2, D1, D2 etc., then compute the Jacobians here, right, then find out if the f of xmf and g of xmf is less than epsilon, right, because this is a straightforward this thing. Then if it is not, then go through the next iteration and take the next value of, you find out h and k from that term, take the new value of xm, new value of f, and ensure that solution should not diverge, it should converge, okay. If it, right, if it diverges you should end, if it you know it does not, you know, it converges you go back. So, you continue this loop, okay. Now, finally, if you get, when these two conditions are satisfied, if these two conditions are satisfied, fxmf and gxmf satisfied, then you compute this print xmf and calculate the results and you know the performance etc. So, this is a flow chart which can be used for solving these equations, okay. Right, I think we have I have already explained to you, this is already written how it is done, and because there was an experimental setup where testing was done, okay, and this is details of experimentation, I think we can skip this, and these were the details of the machine on which the experiments were conducted, okay, these rated values, okay, and Z base and so on, okay. Then we measure, these are the parameters which were measured for one of the machines, and this was the Vg by f curve as I mentioned to you, this is xm and Vg by f for that machine, right. And the performance variation of this, of course, we took Vg by f can be written as a linear equation in saturated mode, okay. Vg where is xm, you can just assume it to be linear. Okay. So, we assumed it to be two straight lines like this, okay. One is saturated, other is non-saturated, instead of all the non-linear one, just to make a simple calculations, okay. This is a linear equation. Of course, the results are presented in that paper, and of course, this is Newton-Raphson. So, this is the result. Load characteristics means as you load the machine, what do you expect? The voltage will come down, okay. This is the voltage which is for different values of capacitors, okay. You will see that experimental results points are close to the theoretical points. So, this is in any research, you know, this is what they expect, your simulated result must be close to the experimental results, right. Only then your worth, your, you know, your paper will be worth accepting in any international journal, okay. It's like worth of the pudding is in eating. So, you must conduct experiment to show that your theory has worked. Okay. Now, interestingly, it is almost like a shunt generator characteristics. Okay. It goes to certain beyond which it bends. Okay. Okay. So, this is the and this is for different capacitors. Okay. This may be for C1, C2, maybe C3, which are given here. Which one will be more? Huh? C1 is more or C3 is more? Because if we have discussed earlier that if C1 should be more than C2 should be more than C3, because for higher the capacitor the voltage will be higher. Okay. Now, you would like to this is the frequency actually. Okay. Okay, I think this is a main of discussions on this. I think we will skip this. There is a frequency does not drop much from no load to full load, but voltage will drop. Okay. So, these are some of the family of characteristics which are already drawn, and effect of terminal capacitor. Now, what is interesting is this is for different capacitors, right, higher capacitor, lower. Supposing I want to maintain the voltage to be constant at 1 per unit. This is a constant voltage line. You do not want the voltage to change, as the load varies you want the voltage to be same. So, what is the arrangement should be? That means at a no load you can use this capacitor C1. Okay. So, at this load you want C1, as the load increases maybe you would prefer C2, and here maybe C3, at this load C4, C5, C6. Is it clear? So, you must increase the capacitance to maintain the constant load. So, if you want V to be constant, for as the power varies you would prefer to have a variation of C, right. This C versus power, right. At no load it will be small c, as a load increase it must be. So, this is basically you must design a VAR control, right. So, this main crux of the problem for this machines to be acceptable is you design a suitable VAR control through proper electronics. Okay. So, either you have a switch capacitor, because everything has to be automatic. So, so this was the main problem where this has been this research of in this area has got little hiccups. Okay. You can have an engine driven system, speed may be nearly constant, but as the voltage varies depending on the type of voltage, as the load varies the voltage will be not be constant. So, any generator will be acceptable only if you maintain the voltage constant. That is the point. In your house also you do not want voltage variation, isn't it? So, the main problem, in fact even I have suggested a few BTech projects or MTech projects also. Somebody makes it, then it can be immediately transferred to the field, transferred to the industry who can make this. So, controller development has become very critical because future lot of decentralized power generation will be there, and this is a simple machine. So, the work that is remaining to be done is to develop the controllers for this, okay, to maintain the voltage constant. Okay. So, this is the effect of magnetizing reactance. Magnetizing reactance, if it is higher the magnetizing reactance, obviously voltage is more, lower magnetizing reactance it will draw magnetizing current more. Okay. This is the variation of this. Okay, I think we will skip this. This is the effect of magnetizing reactance. I think we will skip this, these are all routine. Effect of speed. Supposing it is driven by a wind machine, okay. So, there is a considerable variation in speed, right. Then you would naturally, these were different speeds, say 0.7, 0.8, 0.9, 1, 1.1, 1.2 per unit, as the speed will vary. So, you will have a different family of curves, Okay. So, but your interest is to maintain constant voltage, right. So, you may have to think of a different values of you know capacitors etc., for the different speeds, right. So, you require a suitable controllers. So, we should think of how to do it. Okay. This is the frequency variation. Okay. So, we have seen effective speed will be to increase the voltage with speed, right, and increase the frequency also. So, frequency will also increase with speed, voltage will also increase with speed, and therefore, there is a considerable variations are there. So, you need to develop a suitable controller for this. So, capacitor var requirement excitation 1. So, lot of studies were done, these are available in literature. How much I give you a machine, how much capacitor you will connect. So, there should be a way to estimate that, no, calculate that. Okay. So, this was also a work which was carried out. I mean this, you know, effect of terminal capacitor, and you can have a different criterion. One is you want to maintain the Vt constant at loads, or you can have voltage to speed constant, you want to have flux constant or Vg by F constant. So, depending upon this you must develop a var control. So, basically these are all the different methods in which you can have a var control. So, this was for one of the machines, some studies were made. Okay, these are the family of curves of how much capacitor you require, both computed experimental, okay, for different speeds, right, to maintain what is the var requirement, what is the capacitor required, a different output power to keep the terminal voltage constant, right, at some value, okay, at different speeds. Right. This again var and GC required to maintain output constant, Vt by nu constant. So, there is a different criterion again. This is Vt by nu constant at some value, this is the of course variation of current and output power. The variation of capacitor and speed with output power to keep the flux constant, this is at flux constant mode. I mean, these results are available in literature, I am just reproducing it. This is when you maintain the flux constant, what should be the criterion. Okay. Okay, for this we will skip desirable criteria for voltage regulating systems. Okay. Because then there is another system which has been developed is a single phase generator. See, these are all 3 phase generators. Okay. But your load will be single phase in your house, at your backyard, you know, now most of these portable gensets which are engine driven, they are all single phase generators. So, but there was a lot of demand for this. So, we thought why not we relook at this situation, either you make a 3 phase generator to operate on single phase or make a separate single phase generator. You want single phase load, take a 3 phase generator and somehow manipulate the circuit to get single phase, or make a single phase generator. So, the work was, so single phase is compact, economic, brushless and maintenance free. So, what we designed a specially designed machine with 2 windings. So, we have that machine in our lab, okay, with a die cast rotor, and we connected some shunt and series capacitors. Okay. This is the system. So, in normal mode, this is a specially wound main and auxiliary windings, the windings were different. So, this is the only patent we have, you know, this winding configuration. Okay. This is a normal squirrel cage rotor, okay, and you connect a shunt capacitor here across one winding, auxiliary winding, and a series capacitor in the main winding, okay, and you connect a load. Okay. In fact, for this analysis, so you will see a case in which you have 2 phase asymmetrical, 2 phase asymmetrical winding induction machines connected with asymmetrical external circuits. I think we have done the analysis, is not it, and only thing is here there is no voltage applied, voltage is to be estimated here. Okay. So, this is a sort of a investigation which is not yet been fully completed. okay, because the saturation etcetera are coming into the picture. Okay. This is one of the unsolved problems, right, but we have this is a system which is working. We built this system, this was made, the whole design was mine, okay, and it was coupled to an engine, and this is the control box. Okay. It provides a reasonably good performance. Only thing, somebody has to take this technology and market it, right. This is where it starts, and it is supposed to be cheaper than the existing the machines. Okay. Another option is you take a normal 3-phase machine, you connect some capacitors in this and you connect a load here. Okay. This is another way. Take a 3-phase machine, do some manipulation. This is also one of the other options that, in fact, one has to compare which one is best for this. Okay. Okay, sorry. Now, last aspect I want I will discuss before we close. One is, why are we doing all this? Is that some prime mover is there which will drive this standalone system and which will supply it to the load. So, either you require a 3-phase generator supplying 3-phase load, 3-phase generator supplying single phase load, or a single phase generator supplying single phase load. These are the options, right. And the prime mover depends upon the energy source you have, whether you have hydropower, wind power, oil, biomass, biodiesel. Okay. So, it can be engine driven. Okay. So, one option is engine. Engine, one of the special feature of engine is it is nearly a constant speed. The engines can, it has an internal governor system. So, it is maintained constant speed. There is some automatic power balance is there. Okay. If you want more power, when you drive a car, if you require more power, it will draw more fuel and give you, there is automatic power balance is there, isn't it. So, and the fuels are typically oil, petrol, kerosene, diesel and bio. Okay. Future may be this only. Okay. Now, you have to design your generating systems for this, which is a constant speed automotive power. Hydro uncontrolled turbine, it gives constant power. So, hydro is a constant power, right. So, there is a 10 kilowatts always available to you, must use 10 kilowatt, otherwise you have to burn it somewhere. Okay. So, and it is nearly constant speed. So, prime mover characteristic is different here also. Then another is wind is another ball game, variable power, variable speed. So, as electrical engineers, you will have a challenge in hand, because these are the energy sources which are likely to be futuristic. So, you have to develop energy conversion systems which will satisfy the needs of the consumer. What is the need of the consumer? He must have a constant voltage, constant frequency, and for whatever load he connects. So, you must be able to take care of all the users and abusers of a customer. Okay. Harmonics and all the things are there. Okay. Right. So, you require a proper voltage regulator. Okay. Or okay, let me see, I think we are repeating it, or right, I think we have. Now, in a microhydral system, maybe we will skip this. Okay, I lost practical scheme. I will show you 3 practical scheme before we close. Or it is a hydro system, and here P is constant. As I said, head is constant, discharge is constant. Okay, power is constant, and the consumer, it has a variable power. Consumer requires, he can switch on and off whatever he likes. Okay. Therefore, we have to maintain here also the SCIG power is constant. Now, you have to have an artificial dump power, I call it as PD, which also has to be variable. So, always P should be equal to PC plus PD. is not it? Therefore, the job in hand is to develop a reliable electronic ELC, we say electronic load controller under dump load. So, you should always try to see how to maintain the voltage constant here. Whatever may be the consumer load, the dump load should take care. Supposing this is 10 kilowatt, if the consumer wants 3 kilowatt, what it should dump? 7 kilowatt. If consumer wants all the 7 kilowatt, dump load should take no power, is not it? So, this is the main electronic controller where the work is to be done. Okay. Now, the system which has been developed is you have a generator, okay, which is driven by a prime mover. You have a rectifier here, you rectifier and you have a chopper, okay, and you then this resistance is there, you chop the duty cycle through this chopper. So, if there is no power is required, you make the duty cycle 0, if full power is required, make the duty cycle 1, and this is the device which is used is IGBT. Okay. Till now lot of work has taken place, we have proven it works and it works in the lab. A few things have been put to the field, but we are not 100% satisfied, because in some conditions IGBT will burn. So, you have to develop a reliable controller, so that this is robust, IGBT is safe and a good protection is given. So, that is again the problem in hand. Okay. And this is the result which has been taken in a village where it was installed. So, you will see that voltage is nearly constant for varying power outputs. Okay. So, it is a constant voltage this system is giving, okay. And this is so you know the voltage is constant, and this is the dump power. As the consumer power varies, dump power goes down, right. Dump, when the consumer power is 0, there is a maximum dump power and it comes down, right. And this is all measurements which have taken place, okay, right. And this is a powerhouse in a village which in a micro hydel it has been installed. Now, the plan is some national mission project is underway, where at least about 100 units to be installed. So, we had to have a reliable controllers for this. So, this is the generator which we have designed, okay, and this is the turbine. What is this you have? Belt drive, because it has to increase the speed, okay, and here is the water inlet. Water is coming into, this is the inside the powerhouse, okay, and this is the dump load, okay. So, it is giving, in fact, this was drawn to a few houses in the village, okay. Of course, these are our student, project staff, it was part of a project, okay. Next, this was a load controller which was developed, it is IGBT based load controller, it is inside view of this, okay, which was installed, and I think there is scope for it can be, it is originated analog, we thought we can make it microcontroller based. So, it can be made a more robust and reliable one system, okay, right. And this is the electricity at the consumer's house, okay, and these are basically, I think they are at least classified as tribal. It is a tribal village, where they could not have got electricity in the next 30-40 years, because drawing electricity to that village would have been very difficult. Because we have walked 2 kilometers inside to get into the village, carrying all the electrical load controls. Because one thing is those villagers helped in carrying it on their head, So, this was a very unusual. So, the electricity is going because the light is blowing, okay, in this CFL, right, and they could run their TV etc. from this. So, the villager who are not even 8th pass or something, so they the boys will go and start it in the night, and switch it off in the morning, because throughout the day they are not so much keen, except and of course, these are all the consumers, I mean whom you can call them as tribals, except one, because he is an IIT fellow. He is not a tribal. Okay, right? One of our project staff. Okay, so I think I have taken you from a conceptualization which we started in 1976 or something, and has come to a stage where it is a technology which is transferable, already transferred and more transferable. So, what we are looking forward to now is a very appropriate research in which it can be used for wind system, small hydro system, biomass engine systems, and also other oil engine driven system. So, the generator is there. It is the control aspect which is bothering us. We are not 100% happy. So, it is here that research is need to be done. So, I have taken you to the periphery of the knowledge in this area. So, you must now get sensitized to see whether you can contribute to take it further. Okay. We will close it here on this today. Okay.